Torques occur when forces cause angular acceleration. Now, to calculate the amount of torque so that we know how much angular acceleration to expect, we first have to choose an origin. And the origin is typically chosen to be the axis of rotation. So in this picture, you can see an overhead cartoon of a door, where this is the hinge, here's the door, and then here is the doorknob. Since the door swings about the hinge, we choose the hinge to be the origin. The moment arm, which we've labeled as r, is a vector that goes from the origin to the point where the force is applied. Here we're pushing on the doorknob, and so the moment arm goes from the hinge to the doorknob. The force vector is then also shown, and if the moment arm and the force vector are perpendicular to each other, then the torque is equal to the length of the moment arm times the amount of force. And torque doesn't have its own special unit. The unit for torque is just the unit for this moment arm distance times the amount of force, so it has units of newtons times meters. So that was for the special case where the moment arm and the force vectors were perpendicular to each other. More generally, in order to find the torque, we take the length of the moment arm times the force and then multiply by the sine of theta, because that gives us the component of the force that is perpendicular to the moment arm. And so theta is equal to the angle between the moment arm and the force vector. So if you were to push in this direction on the doorknob, the force vector and the moment arm have an angle of theta between them. And then if you push sort of outward like this on the doorknob, then here would be the angle theta, where theta is the direction between the direction of the force vector and the direction of the moment arm vector. Now, torques change the angular velocity. They cause angular accelerations. And without a net torque, the rotation rate won't change. This is equivalent to Newton's first law in the land of rotation. Now here we see a picture from actually the family photo album. This is my husband's grandfather on the back of this, this forklift thing. And you can see that he understands something about torque. He knows that if he wants to cause this tractor to rotate, that he needs to increase the moment arm. He needs to get back as far as possible so that his weight will be acting with a longer moment arm and cause a greater amount of torque. Although it does look from the picture like the tree's torque is winning. Now, torque is a vector, and of course that brings up the question, what direction does this torque vector point? And the answer is that we use the right-hand rule in order to determine the direction of the torque vector. And the way we use this right-hand rule is that first off, you point your finger in the direction of the moment arm, you curl your fingers in the direction of the force, and then your thumb will point in the direction of the torque. So for example, if we look at this F1 force, here's the moment arm. So if you put your fingers in the direction of the moment arm and then curl your fingers in the direction of F1, then your thumb will point out of the screen. And so out of the screen would be the direction of the torque vector. Here, on the other hand, we have a force vector pointing this way. So once again, if you put your fingers in the direction of the moment arm and then curl your fingers in the direction of this F2 force vector, then your thumb will point into the screen. And so into the screen will be the direction of the torque vector. Another way in which we designate these torque vectors, especially when we add them together, we follow a particular sign convention. If the torque causes a counterclockwise motion, then that is a positive torque. If it causes a clockwise motion, then that would be a negative torque. So let's look at this example image here. If we just imagine pushing with this one force, if we just imagine pushing with F2, then the door would swing about the hinge in a counterclockwise fashion, and so that would be a positive torque. So the torque caused by F2 is positive. F1, on the other hand, if that was the only force acting on the door, it would cause the door to swing in a clockwise motion about the origin, and so that would be a negative torque. So if we were to add these two force torques together, we would have a negative torque coming from this force and a positive torque coming from this one. Now, one question which often arises is, where do we put the origin? In the door example, it was pretty simple. We just put the origin where the axis of rotation was, and that is a very common thing to do. But sometimes it's less obvious where the object is going to be rotating around. And we need to find the origin. We need to choose an origin because the origin determines what our moment arms are, their length, and what direction they point. So, as we previously mentioned, we often choose to be the origin to be the axis of rotation, but sometimes we just don't know where it's going, how the object is going to rotate. So here we have 3 dogs that are pulling on this toy, and you can see their force vectors are in all different directions. Where would we put the origin if we wanted to determine the dog's torques on the toy? Well, it's just not obvious, and so in this case, what we would do is we would pick a point on the object and then just consistently use that point through our example. So the origin, just like with the coordinate system, the origin is something that you choose, and you can choose the origin to be where it makes the problem the most convenient. So here's another question for you. Using a screwdriver, you try to remove a screw from a piece of furniture, but you can't get it to turn. So to increase the chance of success, which type of screwdriver should you switch to?